So that's the coordinate format. Let me talk now about another format called the compressed sparse row format. Very well-known format, probably the most well-known and most used format. So compressed sparse row, CSR format. And we also have 3 arrays in this format. I have to decide how long to make these arrays. Okay, and I'm going to draw the format for this matrix again. The first array is called IA, and these are also known as row pointers. Next array is called JA, and they're also known as column indices. And then the last array is called A, which are just the values. Okay. In compressed sparse row format, all of the entries in a row are stored together. Okay, so the matrix is stored row by row together. So for this example, the first row is 10, 11. I'm going to store that together. The next row is 12, 13. And then the last row is 14. Okay, and for each element, there is a row index, right? The column index. For 10 and 11, they are 1 and 2. And then for 12 and 13, 2 and 3. And the last one has column index 3, right? And then we have a pointer to the beginning of each row. So the first row begins over here. Second row begins over here. Third row begins over here. The fourth row, if there were a fourth row, begins over here. And we need to know where the fourth row begins because that also tells us where the last row ends. Okay? And if we put some index values, so this is 1, 2, 3, 4, 5. Instead of having real pointers, this just says 1, position 1. This says 3, position 3. Position 5, and position 6. Okay, so this is the compressed sparse row format. And I'll also write down the algorithm for multiplying so the algorithm for y equals ax. Okay, so first we're going to loop over all of the rows for I equals 1 to n. And then we're going to loop over all of the entries in each row. Well, let's set yi equals 0 first. For j equals ia I to ia I plus 1 minus 1. So that's all of the entries in the row. And then we can accumulate into the ith component of j, yi equals yi plus aj times x ja of j. So ja of j tells us which component of x multiplies that component of a. So also very simple, but good to see, to understand how the format works. So I want to compare and contrast the two different algorithms. Okay? in this algorithm, the array A is the array A and the array JA. These two arrays are traversed in order. Right? IA is also traversed in order. Right? So we're just going to read these arrays sequentially. Right? We just go through these elements. So J just increases from 1 to the number of non-zeros sequentially. So we traverse these things in order. A and JA, so this is the first point, A and JA are traversed in order. Similarly over here, right? All of these elements are traversed in order. Sorry. All of these elements are traversed in order for this coordinate format. But the elements of X are not traversed in order. Okay, so traversing in order has some advantage for computing because you can predict how memory is going to be accessed. All right, so if things are traversed in order, memory access is predictable. And efficient. The hardware can see that you're traversing the memory in order and start to prefetch the data for you. Okay? So X, however, the vector X, is traversed in an irregular order. The order is going to depend on the sparse pattern of the matrix and may utilize caches poorly. So what is a cache? So let me give you a very simple conceptual idea of what is a cache. A cache is a piece of computer hardware that lies between the main memory and the CPU. Okay, so whenever the CPU needs to operate on data, it needs to fetch the data from memory. But this main memory is slow. It is big, but it is slow. Right? So in between, there is something called a cache, which is also memory. It is typically small, but it is fast. And the cache is designed to hold data that was recently used. Okay, so the cache stores recently used data. So that this data can be accessed quickly. Okay, so it's a little bit like, suppose that you have a favorite pencil. You use this pencil all the time, so you put it on top of your desk, and maybe you have some other pencils that you don't like so much, and then you put them in a drawer somewhere. Right? So normally in programs, whenever you access some data, you might need to access it again. And the whole idea is to store memory that you've accessed recently into small and fast memory called cache. Okay. Now to improve cache usage, so here, so what normally happens, the CPU says, well, I need this piece of memory. It first checks if it's in the cache. If it's in the cache, then that memory gets delivered directly to the CPU very fast. If it's not there, then it has to go to the big and slow memory. And while it comes back, it's going to be stored in the cache. Okay? Now the cache is is small. It has a limited amount of size. So let's look at a particular matrix structure, that particular sparse matrix. So here's an example. So this is a 8 by 8 example. That's not going to be 8 by 8. I'm sure you're having a lot of trouble drawing this. Okay, so I made this example last night. You don't have to draw it exactly, but you will see the point after. So I'm drawing dots where there are zeros. Okay, so this is the matrix. I want to multiply it by a vector, x1 all the way to x8, right? And the result is going to be the vector y. Okay? And let's suppose that I'm going to run this algorithm, the CSR algorithm. Okay? So what is the access pattern for x? I first need to 1, 2, 3, 4, 5, 6, 7, 8. I first need x1, then x5, and then x7. Okay, then I need x2, x4, and x7. Then I need x3, x5, and x8. Okay, so suppose that the cache size is 3. I can only store 3 elements of x. Suppose cache for x has size 3. Okay, so caches are very complicated. Normally we can say for a certain variable we have set aside some cache for it. But let's suppose, for argument's sake, that we only have 3 locations in cache. Remember, it's small, right? So we only have 3 locations that we can store for x. So we store x1, x5, x7. Then we need to store x2, so we need to throw away x1. And we need to store x4. We need to throw away this one. Then we need to store this one. But luckily, we have that one in memory. So we could take advantage of cache there, but we did not take advantage of cache anywhere else. And you can go through and see how often we have taken advantage of cache. So we can try to improve the cache utilization. In other words, we can try to improve the chance that we will find our desired x inside cache. So how can we do that? So to improve cache usage, which means increase the chance that elements of X are found in cache, what can we do? We somehow want to change the order of the computations, right? If we maybe choose different rows, choose the rows in a different order, we might be able to improve cache behavior, right? We might even choose different columns. In other words, instead of going in order like this. Okay, so this just corresponds to reordering the matrix. So reordering the rows and columns of the matrix. Right? So I'm going to reorder the rows and columns of this matrix. And it's another 8 by 8 matrix. And in fact, it looks like this. It's just a tridiagonal matrix. So what I did last night was I made the tridiagonal matrix. Then I came up with some ordering to make the matrix look like that. Okay? So these are the same matrices, but I've reordered the rows and columns. And now look at what happens if I multiply by x. Right? I need x1 and x2. Then I need x1 and x2 and x3. I can store all of those in cache. Then I need x2, x3, x4. 2 and 3 were already in cache. Right? And how do we get, if someone gives us this matrix, how do we get this matrix? I did it the other way. Yep. You have an answer? You can just try to make this matrix more banded by using a breadth first or level set type of ordering, right? So any kind of banded matrix, it doesn't have to be tridiagonal, any type of banded matrix will give us better cache behavior in this vector x. Right? In the algorithm, we needed to traverse A and we needed to traverse JA, right? IA. Those were all traversed in order. So those memory accesses could be very efficient. So what really slows down is these accesses to X, which could be slow. Okay, but if we reorder, we can make good use of cache when we're accessing X. So the idea here is to reorder. We can reorder A so that it is banded, or reduce the bandwidth of the matrix. So this is a great application for RCM ordering. So RCM ordering is not used anymore for reducing the amount of fill-in because other algorithms are better, like nested dissection. But it has a lot of other applications, and this is just one of them. Okay? I think of it as an ordering that preserves or creates locality. Okay, so what I want to do right now is to show you where you can find a source of test matrices that we can use in this course, and that if you ever do research in this area, very useful. Many researchers use test matrices from different applications. And this is the University of Florida sparse matrix collection. It's available on the web, but I don't know the web address. I never type in the web address. I just search for the name and I go to the website. And it contains thousands of test matrices from different applications that people have submitted. And in fact, if you have a test matrix, you're welcome to submit one so that people can see how well their algorithms work on your matrix. So I'm going to show you this in a moment. But I want to write down first how you access matrices from this website. So there are two ways of downloading matrices. So the first is to download directly from the website. And if you're using MATLAB, there's a .mat file. So something .mat file that you can just download from the website, right? And then from MATLAB, at the MATLAB prompt, just load your MAT file. That's going to create a variable called problem. And to get the matrix, you say A equals problem .a. So problem is a structure that contains lots of other things, one of which is the matrix. And then the other way you can download matrices is using a function in MATLAB called ufget. So directly from the MATLAB, so you don't have to download any files. Directly you just say ufget the matrix, and matrix is either the name of the matrix, which you find by looking at the website, or the ID of the matrix. And each matrix has a unique ID. The second option is very useful if you want to download lots of matrices. Okay, so let me show you what the website looks like. Thank you. So I was going to talk about MEX files, but I don't have time to talk about MEX files. Here's what the website looks like. Okay. And these are pictures of the sparse matrices. Very weird because they don't look like matrices. So these are artistic representations of the matrix, of some of the matrices on the website. So how were they generated? So normally so a lot of these problems come from finite element or finite difference discretizations. But when you submit a matrix, you don't submit information about the grid points. So the people here don't know what your matrix is. I mean, don't know what the geometry is. But there's a way of trying to reverse engineer what the geometry is. So that's what they've done, is they've taken your matrix and said, well, we think that it is something that looks like this. Okay? So you can go to this website and you can search in different ways for matrices that are of interest to you. And you can download the matrices in different formats. One is the MATLAB format, which is the one that I like to use. But there are other formats that can be used for C programs, for instance. And here's an example of how to use ufget to get your matrix. Okay, so I don't have a live web connection, but you can try this on your own later on. But I downloaded some matrices earlier that I can show you, and then I'll give you a short exercise for you to do involving downloading some of your own matrices. Okay, so here's my MATLAB. So earlier I downloaded, I think I downloaded this matrix called Apache 2. Okay, so I'm going to write clear all, and if you download Apache 2 directly, the first option, right, you'll see that there's a structure called problem, and problem is a structure that has a number of fields, many of which describe what the matrix is, but one of the fields is the matrix itself. It's a matrix that is 715,000 by 715,000. So A equals problem dot A dot A. Okay, so now we have the matrix. We could try to look at it. Okay, it looks very banded. It looks very banded because the matrix is very big, right? But if we zoom in, which you can do in different ways, you can see that there's quite a bit of structure there. And then the other way to download matrices is to use ufget. So problem equals ufget, and use the ID. And you can type in some ID. You can find out what is the ID from the website, or you could put in a name. So again, one advantage of using ufget is that it will store this matrix for you on your computer, and next time if you want to get the same matrix, it won't download it remotely. It'll just get it from where it has stored it. Okay? Okay, so since we have a few minutes left, let me give you an exercise to do involving downloading some of these matrices. So I'll just turn off the screen. So next time I'm going to try to leave more time to do some computer stuff. So here's an exercise. So download some SPD matrices, so symmetric positive definite matrices. Okay, so there's a way of choosing them from the website. From the University of Florida collection. And you can either download directly or use ufget. If you use ufget, you have to install ufget yourself. You can just download ufget from the same web page. Okay? And then compare the number of non-zeros, which you've kind of done already, in the Kleski factors. Using two different orderings, using RCM and Cuthill-McKee ordering. Okay, so last exercise you were using RCM on some finite difference matrices. Now we'll try it on some matrices that you download from this University of Florida collection. And we're going to download lots of other matrices later on to try different exercises. So we don't have Cuthill-McKee ordering, but that's just reversing the reverse Cuthill-McKee ordering. Okay, so if we say that P is the RCM ordering, then Q is the Cuthill-McKee ordering, and you can get it from P end colon minus 1 colon 1. So this just reverses the ordering. Okay. And then compute the Kleski factor. And this is why you're downloading symmetric positive definite ones, because you want to make sure that you have a Kleski factor that exists, or that you can compute a Kleski factor. Okay, so compute the Kleski factor and print out the number of non-zeros of that Kleski factor, and then similarly do the same thing for Cuthill-McKee ordering. Okay? And what you can do is to make a table, maybe do a few matrices, RCM, number of non-zeros, and Cuthill-McKee, number of non-zeros. And the question is, how much worse is Cuthill-McKee? Is it always worse? Okay. And if you find a case in which RCM is a lot better than Cuthill-McKee, then that's a case in which you can try to find why RCM is better. And you can do that by using SPI to look at the matrix, to compare the patterns. And the belief is that in RCM, you're going to get a lot of little structures that look like downward pointing arrowheads, which we know which are structures corresponding to less fill-in. And the reverse ordering of that are structures with upward pointing arrowheads, okay, which has more fill-in. So this was the observation initially that said, well, I looked at your Cuthill-McKee ordering. It looked like you had all these arrowheads. If I just reverse it, I should have less fill-in. Okay, so this doesn't always happen, but try to find some examples maybe in which it does, or maybe you can't find any, I'm not sure. But it's an interesting question. I've never done this myself, to really try to understand what is the difference between RCM and Cuthill-McKee. Okay, so that's it. I'll see you tomorrow. Have fun with the exercise.